Hello and welcome to yet another video on some basic C# with the intention of building us up to working in Unity with our C#. In this video, I'd like to go over some basic arithmetic that you can perform with data types that we covered in the last episode. I expect this video is going to be a little bit short by comparison to the last one. It was a bit of a 35-minute doozy. So first of all, I'd just like to point out that when we're working with integers and floats, you get different behaviors when performing arithmetic. For example, if we look at integers, we'll say int result is equal to 32 plus 5. Actually, you know what? I'm going to change this to be addition result. Now, I'm also going to print the result. So right line addition result. Here we go. Let's see what happens when we run this. Now you can probably assume that this is going to give us the number 37 in the console, right? Now, addition and subtraction are pretty simple in terms of what they do. And you can reasonably believe that the same thing is going to happen if we were to swap these. Why am I using the literals? So let's say float 1, float 2. I'm going to have to change my types to float. And reasonably so, we're going to get, you know, some pretty expected results here. Similarly, we can do the same sort of thing for multiplication and division. I'm just going to quickly write this out here. All right, so here I've just cleared everything we had before here, and I've rewritten float multiplication, float division, integer multiplication, integer division. And you'll notice up here in my variables int1 and int2, I've set them to, well, they were always the values 32 and 5, but float 1 and 32 are now equal to 35 in float and 5 in float. So let's watch what happens when we run this. Now it proves that basically you're getting the same results that you expect, except what I'd like us to look at here is when we're dividing int1, 32, by int2, we're getting 6, despite the float version giving us 6.4. Now the reason for this is that the value of an integer divided by another integer, even if that second integer doesn't fit into the first one an even number of times, or I should say a whole number of times, we truncate the remainder of the result, so the 0.4 in this case, so that we can store the result back into an integer. And that's the way it works. We're really concerned about how many times int2 fits into int1, and then we discard whatever it remains after we've done so. And this brings us into the modulus operation. And the modulus operation is essentially a form of division, but we don't actually care about how many times a number fits into the first another number, but rather if we were to fit a number into the first or second number, let's say into the first number as many times as we can. I'm going to change this from division to modulus. And I'm going to change the operator here to this, a percentage sign. Modulus result. Check out what we get as a result of this. It gives us 2. So what this essentially signifies is that 5 fits into 32 a number of times. We know it to be 6 from our division. This is the remainder, the portion of 32 that doesn't fit into an equal division of 5. So that covers modulus, which has some interesting uses, which I hope we'll get into later on. So the next thing I'd like to cover is iteration and deiteration, which are actually a form of addition and subtraction. So let's say we have an integer. Int is equal to, let's say a, and a is equal to, well, it doesn't matter. Let's say 10. Now, one way to write int is equal to, or is equal to a plus 1. And you know what? I'm actually going to add our right line here. So, and also, okay, we've covered all this. I'm just going to delete this right away so that we're not getting a bunch of messages we don't need. So it's 11, right? 10 plus 1 is equal to 11. Another way that we can write this is simply a plus plus. And that is the whole statement. That is the whole line. See? And now the use of this is that when we're talking about a on the left side here is equal to 10, our integer literal on the right side, a can't really be mutated in this sense. Like we can't like say int a plus 1 is like, this doesn't make any sense. A here with the plus plus trailing it, this is called a postfix, by the way, actually can be read as a right-hand attribute here. So for example, int b is equal to a plus plus. And I'm going to write right line b here. Okay, we got 12 because, wait, no, a is equal to 12 because essentially here what we're doing is we're modifying the value of a by increasing it. So this is actually modifying the value of a, and then we're taking the assigned value of a, assigning it to b, and then calling b here. So b doesn't see the change that has just occurred to a. And the reason why this is actually in the syntax. Int b equals a plus plus means int b is equal to a, read the value of a, and then when all reading is done from this right side here, then increment the value of a by 1. And you can think of it as these two pluses appear after the a, so the plus plus operation, the increment, happens after the value of a has been read. If we want to change this behavior, we actually have to put the plus plus before the a. And now this is a prefix iteration. Now, I'm going to close this out and run this again. Check this out. Now they're both 12 because int b is taking on the value of a after the assignment has been done. And we know that the assignment was done before the value was read because the plus plus appears before it. I hope that makes sense. Please feel free to review this if you need to, but prefix and postfix is very handy. It allows us to do a great deal. For example, let's say I didn't want to be using b at all here, and a is still equal to 10, but I wanted to add 1 to a here. Now, what's going to show up when we print right line in the console? If you said 10, that's correct, because remember, we're reading the value of a before the iteration has occurred. If we want the increase in value to happen before we sample the value of a for the purpose of writing out to the console, then we have to put it beforehand. And now you can see we have the value of 11. In a similar vein, although this isn't quite the same, what we can do is avoid a case where, let's say we have int is a is equal to 10, a is equal to a plus 2. So an increment using plus plus isn't going to serve us here because we're increasing by a value that's not quite 2. Now, there is actually a way that we can shrink all of this together using what's called a compound operator. The compound operator looks like this. An important thing to remember, I'm just going to add back our right line here. An important thing to remember is that in a compound operator, the equal sign is always on the right. That's how the compiler knows that we're not just assigning something like to a on the left. This actually isn't going to throw an error here because this is just really saying a is now equal to plus 3. If I run this here, you see a has been set to plus 3. But the other way, on the line right before it, the plus before the equal sign, is incrementing our value of 10 with 2. And this works for any of the operations we've covered so far. So for example, a divided by 2 is going to give us 5. A modulus, let's say 3, or compound modulus is going to give us 1 because 3 fits into 10 3 times. 3 times 3 is 9. 10 minus 9 is 1. And that covers all of the main arithmetic operations that you're going to need. For the rest of this video, I'd just like to cover some special cases, such as, for example, what happens when I'm going to set a is equal to 10 divided by 0. Now, the compiler is not even going to let this compile because division by 0 is not possible. I'm going to try to trick this a little bit by setting 0 to a value here, and then divide by the value of 0 here, or reference the value 0. All right, and see, attempt to divide by 0. It's not going to allow us to do this with integers. You cannot divide by 0. It is just an illegal operation in mathematics. Now, you might think that that's going to stand true for floats as well, but check out what happens here. We got the value of infinity. Now, this is an approximation. In mathematics, you cannot divide by 0. However, what is happening here is that the floating point value of 0 is being taken as an approximation for a number that is arbitrarily close to 0 from the positive side. And so this isn't causing the program to stop running. Rather, we're actually getting the literal value of infinity. So floats can actually, in addition to being equal to a numeric value, they can be equal to infinity. In fact, if you wanted to ever reference the value of infinity directly, you can do so using float dot infinity, positive infinity. There's also negative infinity in here. If I run this, we get the same result. There is one exception to this behavior I'd just like to cover quickly, and so this is what we've seen so far here is going to always be true for floats and doubles, but decimals have a slightly, S there, has a slightly different behavior here. I'm actually just going to keep the variables called float, just for no particular reason. But let's say we take float 1 and we divide by 0m, so the decimal literal of the float. Now you would expect this to give you infinity, but actually decimals every time are going to throw an exception claiming that you have attempted to divide by 0. And this is because decimals attempt to be accurate, even though floating point numbers can only achieve such a degree of accuracy that gets you like pretty close to the number that you think that you're storing. Decimals, whatever the case, dividing by 0 is going to give you this issue. It doesn't matter whether this is a literal or a reference to another number. If it ever happens, it's considered to be not what the user intended, because decimals are very good for scientific applications due to their precision. Now, the last topic I'd like to cover today is what happens when a variable overflows. To keep this brief, I'm going to use a byte to express this, but the same sort of thing happens pretty much no matter what the data type is that you're dealing with. So my byte is equal to, and we're going to set this to, 250. Now my byte, I'm just going to write this out, let's say about so many times that we're going to go over 255 here. Now we're going to run this. Okay, you know what? I'm going to do a console write line here after we've changed the value here. And actually, what I should point out here is that in C#, anytime you sort of hit the enter key or create a new line, you're not actually influencing what is seen as a statement or not. You could write your whole program on one line if you wanted to. In some languages such as Python, that's not the case, but in C# it is. So in this instance, just to keep things a little bit simple, I think it's a little bit cleaner to write this all in one line as opposed to just having a bunch of little blocks like this. So that's what I'm doing. Just a little aside. So let's run this and see what happens. Okay, so we counted 251, 252, all the way up to 255. And then the next time we added a number to my byte, it rolled over to 0. So it essentially fell off from being in the position of the highest possible stored value that you can have. And then it restarted from the left. So you got to be careful when you're working with integers. If you try to add a number to an existing number, and that would take it over the maximum storable value and start counting back up from there. In the case of a signed byte, I'm going to change this to 125, let's say. And I'm going to demonstrate this now. It does the same thing. It goes past 220 or 127, sorry, and then rolls back over to the next value from the far left, which is going to be negative 128. Now, as a final thing that I'd like to look at, and I know I said final already, this is the final for the floats, okay? For floating point types, whenever we're going to get into a rollover situation here, we get something that happens a little bit differently. So here, what you can see is I have a float, which I'm actually going to rename to my float, is equal to float.max value. And max value here is equal to 3.4 times 10 to the power of 38. So a very long number. I don't care to try to figure out what it is or write it out longhand here. But what I'm going to do is I'm going to multiply this value by 2 and try to store it in the same variable here. Now so we're obviously walking into an overflow situation, similar to what we were seeing with the integers, but let's see what happens here. And we just got infinity. So when we're talking about floating point types, when we sort of go off the end of what the float can store, we reach positive or negative infinity. It doesn't run back to a negative number or anything like that. The behavior is completely different. So I think that probably wraps it up for this episode. If you like what you see, please hit the like button. If you want more of these videos, please subscribe to encourage me to put more out. And thank you very much for your time, and you have a good day. Bye.